Hey there, folks. Let me get a little bit of this stuff put away. And let's see, let me get this stuff out of here. And let's start talking about what happened today in class. Now, today in class I was actually able to lecture a little bit to you about the stuff we're going to talk about. In fact, I did a little background work on the logic, talking about conditional statements, what a conditional statement is. We're going to use a lot of conditional statements in the course of proving things, and I went through a little discourse on, if blah sub 1, then blah sub 2, what does that mean? Well, basically the meaningful part of this, if the condition part's false, it's true by default, and I think the example I gave is, if you wash my car, then I'll give you an A for the course. If you never wash the car, then there's really nothing to talk about, right? It's true because you never tested it. This statement will be true or false. It'll depend on this condition part if the first part is true. We test it. If the test comes out okay, it's a true statement. If it comes out false, it's a false statement. So that's what we're going to set out to do. In many cases, we're going to say, okay, let's assume the condition and show that through a chain of if-then statements, if this, then that, if this, then that, if this, then that, and so forth, we get that this blah sub 2 stuff has to happen. And we also talked about how we could conceivably take that conditional statement and rewrite it as an equivalent conditional statement called a contrapositive. That's where you switch the if-then parts and you negate the if-then parts at the same time. That gives you an equivalent statement. So equivalent to this statement would be the statement, if not blah sub 2, then not blah sub 1. Okay. Oh, and excuse me, I forget I'm kind of doing this in a couple different ways. Then we talked about the biconditional statement, which is basically two conditional statements that each have to happen. And what that really does is establish an equivalency between the blah sub 1 and the blah sub 2. If they're both true, then it's a true statement. If they're both false, then it's a true statement. So that shows that when one happens, the other has to happen. When one doesn't happen, the other cannot happen either. And we talked about direct types of proof, and I was getting a little short on time, so I didn't spend a lot of time with this. But I'm sorry, I'm I'm kind of new to using this system. It's been a little while since I did it, but okay, never mind. So we talked about how you could have a simple direct proof of something where you have this chain of if this, then that, if this, then that, and if then that. And many things we do will be very straightforward, at least starting out. You can, however, find yourself in situations where you're better off by doing an indirect proof. One is to do a direct proof of the contrapositive. One means of doing an indirect proof is to take a look at the contrapositive and prove that directly. Okay, it's indirect because you're not dealing explicitly with the original conditional statement. You're dealing with the contrapositive. Or you could also look at the doing a proof by contradiction, where you say, okay, let's let the condition happen there. But suppose that the then part doesn't happen. And then you look at how that forces the original statement to somehow not happen, which causes a contradiction. Okay? And we spoke a little bit about how to prove a statement is false, and that is by providing a counterexample. If you can provide any kind of counterexample, then you've pretty much shown that a statement's not going to work. So I spent a little bit of time at the end of the day talking about the integer, what we mean by an integer being even and odd. And really we can directly define those things in terms of, putting them in some format. If an integer is even, then I can take some integer k and write that as 2 times k. And if it's odd, I can take some integer k and write it as 2k plus 1. Okay. Now in contrast to that, there's the notion of a number being rational. Okay. Now rational, we can show its form directly. We can say, well, then I've got some integers a and b not equal to 0, such that n is a over b. That's really what we mean by a rational number. It's a ratio of two integers. But we don't have a nice way of representing irrational numbers. We just basically have to say, well, it's not rational. I can't do that. And one other thing that I meant to define, because it's going to pop up in our homework, which, make sure I've got those numbers written down here. Yeah, good. Is the notion of the floor. Okay, I'll dip out of the camera here for a second while I'm writing. The floor of a real number x okay, it kind of looks like the square brackets that we use for matrices and things, but you're leaving that top line off. Okay, this is greatest integer n such that n is less than or equal to x. Okay? And so, just an example, the floor of 2.5, for example, is 2. Because that's the biggest integer I can find that is less than or equal to 2.5. Okay? The floor of three will still be 3, because 3 is less than or equal to 3. Okay, so that's what we mean by that. One thing that is certainly true then is that if n is equal to the floor of x, then there exists a real k between, could be 0, but definitely less than or equal to 1. Such that n plus the k give us the x. Okay, so when you think about it, 2 being the floor of 2.5 just means that I can find some real number, k, that I can add to the 2 and get 2.5. Well, 0.5, right? Some real number between 0 and 1. And here, in this case, the thing I would add to the n is 0 to get that. Okay? This will come in useful to you in the problems that appear in the homework. The only thing I wanted to just do very quickly, and I kind of ran out of time today, but I want to get a good amount of talking in, and then I want us to spend some time proving things to just give some examples of a direct proof. So let me throw in an example. And this would be an example of a direct proof. Let's say that I want to prove something like this. That the sum of two even numbers is even. Okay? You can do this directly by saying, okay, let's have two even numbers, and let's write them in the even number format that we talked about just a little bit ago. Maybe something like m and n. And there exists integers, maybe, I don't know, p and q, I don't know. I don't like that. P and q, such that m is equal to 2 times p, and n is equal to 2 times q. You can't use the same integer for both, right? Because if you do, you're saying they're equal, and we're not making that assumption. Okay? Alright, so that's simply using the definition. Then, the direct proof is we say, oh, well, then let's consider the sum. So then m plus n is 2p plus 2q, which is 2 times p plus q. Right? And since an integer plus an integer is an integer, then that's an integer times 2, which means m plus n must be an even number. So we do a little English here to say that, since p plus q is an integer, then m is an even number. Okay. Dot, and then I said sometimes we'll put a little box there to say, all right, enough of that. Okay. Oops, I don't know what I got into there. Excuse me. Back. There we go. All right. Let me get this off here for just a second. Okay. An example of an indirect proof. Let me get a... blank piece up here. For an example, let's do something like this. And this would be an indeliberate, I can't spell, sorry. Oh, and I also can't start that over again. I am kind of working on an iPad on one hand, talking on another, so I'll get better at this as the semester goes on. Here we go. Yeah, that's looking a little better. Let's do a indirect proof, and we'll do it by contradiction. Or, I'm sorry, we'll do it by contrapositive. Can't spell. And let's say that what we'd like to prove in this case is, let's say that suppose n is a rational number. If m is an irrational number, then m times n is irrational. Okay. Now, I throw these irrationals in because I told you this is a great opportunity for us to turn things around and negate, say, not irrational, which means rational, right? So we can do this actually, if we're going to do this with a contrapositive, we kind of state that. We do have the given, let n be a rational number. Thus, there exist integers a and b not equal to 0. Okay, and that's just the definition, okay, of what we're talking about. What we can do here is say, consider the statement, and let's do now the contrapositive of this if-then statement. Consider the statement, if mn is rational, then m is rational. Okay? So we are then going to let Mn be rational. Which means I've got two more numbers. How about P and Q? And I'll start to use a little bit of this notation. Then there exists P and Q. Actually, let me say a little better. There exists integers in Q. Q not equals 0. Such that Mn equals P over Q. Okay, period. All right, so I think you can see where we're going with this one. N is A over B. So we have M times A over B equals P over Q. And, well, you can continue the sentence or put a period, and I think I'll just put a period to make it. Then what you can do is now is solve for M, right? Multiply by the reciprocal, and it has a reciprocal because, oh, I guess there are some cases here. If then a couple things you got to worry about. If A is 0, then Mn is 0. Oh. Yeah, I guess I need to... I hadn't thought about this. I guess I need to make N be a non-zero. That's a good point. Non-zero. Okay, well, I caught a little mistake there. And so this means that not just A and B, not just B, but A and B, excuse me. Okay. Sorry, I left that part out. I was just moving through and didn't think about it. So let me actually then get rid of this business. We'll not consider the two cases. I don't think it's true if I let N be 0. Okay. Then it's not true, because if N is 0, then M times N is 0, and that's rational. So it's not going to be true unless I let N be non-zero. I'm glad I caught that here. Okay. Then, but if A is not 0, then we can certainly just multiply by the reciprocal, right? Then M is equal to P over Q times B over A, P B over Q A. And then a little statement. Since QA is non-zero now. Q's not 0, A's not 0. And since both PB and QA are integers, then M is a rational number. Okay? So that's what that looks like. And I'm sorry I left that part out, since suppose is a non-zero. There we go. Didn't catch that the first time through. Sorry. You could also do this with a proof by contradiction. Okay. So maybe we do another example. This time we'll do the same statement, but with proof by contradiction. Okay? And I do this just to kind of show the difference between the two. Okay? Now, we would start with the same statement. Suppose n is a non-zero rational number. Then you've got integers a, b is not equal to 0, a is not equal to 0, such that that happens. So that's part of your given here, right? So I guess we just restate that. Let n be a non-zero rational, and there exists a b not equal to 0, b not equal to 0, so that n equals a over b. Okay, which is what we said up top. Now, what we do here in a proof by contradiction is we say, okay, take the result and assume the exact opposite. Okay? And this is the pretend part, you know, suppose that Mn is rational. And you can see the similarities in what we're doing here. Then there exists P and Q. Q not equal to 0, such that Mn equals P over Q. And so it's very similar, right? Then we know that M times A over B equals P over Q, and M oh, and I guess I should have said suppose. Oh, I did. You got to assume the if part. So the part I'm leaving out here is let me just back up and do it right. Because you do have to state that if part. I'm sorry, I'm getting a little of the rust scraped off of me too. But we'll get there as we go. Let M be irrational. Crucial statement. I got to put that in there. Now, here's the imaginary part. Suppose, or not imaginary like an imaginary number, but let's pretend for a moment. Suppose Mn is rational. Then there exists Q. Q not equal 0, such that Mn equals P over Q. And that means that M D, this looks very similar. And then M is equal to PD over AQ. And then you would have the same sentence that we use right here. Well, okay, since, and I guess I wrote them in a different order, but big deal. Since AQ is not 0, and these are integers, I'll kind of skip that. Since the important part is then M is rational, comma, a contradiction. Thus, the original statement is true. Okay? And this is where you put the little box over here, like so. Okay? All right. So there's a few examples that we didn't get to do in class today. For your homework, what I'd like you to do is go to Chapter 2, Section 1. And do all the problems 2 through 11. Skip 12 and then do problems 13 and 14. And what I'd like to do then is spend class time on Thursday trying to work through some of these problems. Now, my expectations for Thursday, I'll be honest, are not high. We've got to get in the habit of doing this, but part of the way we do it is by practicing. Okay? So don't get too upset if it's coming kind of hard or you're having trouble. Definitely do feel like you can come by and see me if you want some help on these, and I'll try to help. And then we'll start to work a few problems on the board on Thursday. Okay? Have a great time fooling with these. I think you'll find they're kind of fun. It's not that bad. And I will see you later.